Well, first of all, thank you very much for the invite, and thank you for having me here. It feels, I've been here 3 times already this year, actually, working with Abdul. We worked together in Arizona. I'm very proud that he was my student there, Robin, my student there. And I gave a lecture here, or a seminar here. Stan reminded me where, about 6-8 years ago when Barry was here, I came and gave a lecture here as well. And so thanks again for having me and having me back, and particularly for the Havlicek Memorial Lecture. And so thanks. So what I'm going to talk to you today about is an idea. The idea is a paper. You have it. I'm to be quite honest, it's an alternative idea, a way to look at something. I'm not quite convinced myself that it's a better idea. I think it might be. This may seem odd. I think it might be. It's certainly an alternative and different way to look at technological change in crop yields. And it's a lot more in line with what I would say the plant scientists would agree. Whenever I've talked to them about this idea, they kind of lap it up. But it's different enough that I'm not exactly convinced myself. So I'd love your feedback on it. Did any chance anyone read the paper? That's all right. It never happens at any seminar. So that's okay. Anyway, so this is really on measuring technological change, and the idea being is that when technological change happens, we as economists kind of look at yield data, and we kind of draw a line through it and have a distribution, and that just kind of moves through time. And the reality is technological change, I don't think, and from talking to plant scientists, can really be measured in that way, in the sense that when technological change comes in, new crop varieties, tools, methods, whatever, it changes the distribution. It affects certain subsets of the distribution, mass in the lower tail, for example, or things like that. And so I'm not so sure the way we measure it really does it justice. And so I'm looking at sort of measuring technological change in different parts of the distribution and measuring it differently, so that there are different rates, basically allowing for different rates of technological change across different aspects of the distribution. And as I said, that's a lot more in line with the way plant scientists who may be coming up with new crop varieties, seed varieties, are thinking about this and things like that. And so in the impacts of measuring technological change, we use it for all sorts of things: food sustainability, economic growth and development. You know, we're measuring technological change in agriculture in many different areas. And so I think it has some importance on that. World hunger, energy, the issues of energy, mitigation of potential climate change effects. And so I think it's an important issue. There we go. And so here's just an example of what we do normally. Okay, we look at some yield data. Okay, we measure technological change. You know, we can use an ARIMA model. We can use whatever. We basically, as I said, kind of just draw a line through it, and this is what we get, and we say the rate of technological change is blah blah blah, and that's what's commonly done. And what I'm going to show you is a bit different than that. So technologies, as I said earlier, are often targeted at subsets of the yield distribution, and when we go into the crop science literature, we see that. We see that there are a number of technologies being introduced, and what they're meant to do is essentially try to move mass from one part of the yield distribution to another part of the yield distribution. Okay, so we have such things. I'm not sure if you've heard of these, and again, I'm not a plant scientist, so you couldn't ask me too many questions on triple stack seeds. But essentially, triple stack seeds are meant to increase resilience to pests and high winds. So basically, what's that meant to do is move mass from the lower tail towards the middle or upper tail. Okay? Racehorse seeds. These are meant to increase top-end yields under near optimal conditions. So essentially, when there is going to be sort of weather conditions or whatever, such that we're going to get a realization from the top end of the yield distribution, it might push that out more. Okay? So essentially, it's a bit different than what we've looked at it when we're trying to measure technological change or predict it, as just what we had before, drawing a line through and then, okay, this is what it is next time. So, question?
So, with the classic green revolution, short stature wheat and rice varieties fit into the racehorse category then? Because optimal conditions, these varieties did better under irrigation with fertilization.
Right,
the traditional varieties didn't do. They did no better than the traditional varieties under non-irrigated conditions.
Right. I would agree with that. So what I'm trying to get at here is, yes, and I would agree with that, is that it's not just shifting the mean up, how we kind of measure it. How when we draw a line through there, we just say, oh, okay, it's just shifting the mean up. I think it's altering the distribution more than that. And I think there's some interesting questions we can ask about that and how that happens that I think are relevant for economics. So what I'm trying to say here is that possible that the rates of technological change are different across different subsets of the yield distribution. Okay, if we think of them as different components make up the yield distribution, then the rates of technological change are different. So for example, the top subset or top component could increase faster than the bottom. Okay, and technological change could also, what I just talked about, change the probability of you getting a high-end yield versus a low-end yield. It's shifting the mass. And so, interestingly, is maybe we can model this and kind of ask these questions, okay? Particularly relevant with climate change coming up. You know, maybe we can separate the yield distribution into different components, and then we can start asking, you know, questions of extreme yields. We can start asking questions of is climate change affecting the rate of technological change in the lower versus the upper component, things like this. So, okay. So here's kind of the idea that I'm looking at. This is just an example, Adams County, Illinois corn. Probably should have picked Ohio, but sorry about that. Oversight on my part. But anyway, here's what we would normally draw through. Okay? And here's what I'm going to propose today, is essentially modeling the yield distribution as a mixture of components. Okay? And then inside those components, measuring the rate of technological change. And testing to see if the rate of technological change is the same in those components. Okay? Which then we would get a line like this and this. They'd be just parallel. And also looking at to see if the probability of those components are changing over time. Like ideally, hopefully, I'll tell you what I was hoping to find. I was hoping to find the probability of the lower component to be reducing over time. Because we have technology, things like that, that should reduce the probability of a bad outcome. Okay? So I was expecting to find something like that. I didn't. Part of the reason is when we're modeling things here, we're using yield data. So I should note, we're not really looking at the portfolio of technologies. We're just basically measuring adopted technologies, right? Because yields are the result of adopted technologies. So.
Now, how does this relate to Chambers' idea of kind of upper and lower envelope of technical change?
That there are two components?
The upper, you could have the whole convex hull of the technology, and the upper part and the lower part might switch separately, or have you connected that to that?
No, you know, I'm going to have to look at that, but from what you just said there, it's not very dissimilar at all. Is it like a regime switching different states? Is it like a different state?
This is really much more simple and stylized than this, so it's not.
Oh, okay.
Yeah.
Okay. I'll have to look at that to see. So, no. Anyway, so basically in the literature, what has been done in the past is linear trend, piecewise linear splines, you know, basically all of these estimating at the mean. In fact, Mario gave me some money to do this for him, if you remember.
I don't.
You don't? Wow.
That's what you get.
I don't know. I think I did. You used it in your whatever that thing was. So anyway, geez, Mary, that's embarrassing.
It was a pivotal point in your career development, is that right?
You know what? It was. I was a brand new assistant professor, and Mario helped me out with some summer money, gave me money. I think it was maybe abusive, not a lot of money, and I did all this work for him, but anyway. But I was an assistant professor, so I did.
Abusive, that's the way I like to work.
Right. So, so yeah, I mean, looking at trend over time of the crop yields is, there are many approaches in the literature and things, but this is quite a bit different. And again, like I say, I think about the idea. It's a very different idea. Anyway, and this is tied to the yield distribution, okay, modeling yield distribution, and there's been a ton of literature in that. I would argue too much, to be quite honest. I think even though I do a bit of work, or more than a bit of work in this area of crop insurance and yield distribution, I think that there's been too much work in the area for the payoff, to be quite honest, by our profession. But anyway, so there are many different methods used. I'm going to get at this mixture of using mixtures to model these different components, but inside that allow me to look at the different trends inside those components. And that's where I think the innovation is, and I think it allows us to ask some interesting questions that we really can't ask, and relevant questions that we can't ask otherwise. So, basically our approach, our approach, if you saw the first page, which is, 9 slides ago, this is joint work with the master student. My apologies. Tor Tolhurst. And so this is work with him. In fact, this became his thesis. This was his thesis. Actually, one of 2 papers from his thesis. So this is, anyway, so I apologize for that. So our approach was to empirically model, to simultaneously estimate states and their parameters, including the technological change. And so that's what we're trying to do here. And we don't have to, when you look at the yield data and you're trying to, I want you to get away from this idea, it comes up whenever I give the talk, is that I have to go ahead and define that this yield belongs to this state. I don't, okay, and I'll explain that a bit more. So we don't really have to go and say, okay, this is from the lower component, this is from the upper component, and you're going to go and measure and look. So I don't need to do that econometrically. So, but allows us to look at these 2 questions, which I think are neat. Test to see if the rates of technological change in the lower component of the yield distribution is the same as in the upper component. And test to see if the probability of states are constant over time. And I should point out, it'll come up, that I'm only looking at 2 states. We only have so much yield data. Ideally, I would presume there are multiple states, but because of data limitations, I've just expanded it to 2, which is quite common when you look at mixture modeling in anything. They write it out as if n goes to infinity, but then when they apply it, it's 2. Okay? It's like polynomial expansions. We had this literature 30 years ago. We were doing these Fourier series expansions or whatever, but it's 2 or 3, right? Okay, so I'm no different here. I'm just going to be using 2 questions.
States are technological states?
Yeah, states, that's why I like to say it's weakly defined. I'm modeling this thing as a mixture of 2 components, or two states. And so the yield distribution is made up of these 2 components. And so that's what I'm referring to states. I kind of like to look at it personally as I'm looking at a yield distribution, and this is not uncommon for a yield distribution to look something like this. And so the parent distribution looks something like that. And I kind of figure it as, okay, this is the lower component, kind of a poor weather state happened, and this is a regular year. Okay, that's kind of how I intuitively think about it myself. And in almost all things we estimate, it shows up that it's a lower component,
Okay.
right? And so yeah.
So
Question?
Does this have linkages to latent class analysis, which is becoming popular in the stated preference literature, where you've got unidentified latent classes and
Well,
it's a mixture of the two?
Right. Yes, it is. It's very much, right? Because I don't identify, and I don't have to identify, right? And that's similar.
And this is also related to the state contingent production function stuff.
This is where you're getting at with
Model.
yeah. I don't link it to that, but yes, it's like, okay, you have two outcomes under different states. But again, this would be, I'm just down to two. You know, you could look at this a lot more, but the data doesn't allow you to go much further than that. So, okay.
Yeah, I was wondering.
Yeah.
What would be the cost of benefit of going one step further and rather than being agnostic about the states, trying to relate them to, say, rainfall? So there are years of low, look at that picture. It's one about years of low rainfall and high rainfall.
Yeah. No, I've done that. So not here, not here. But okay,
So
what
why
we've
is
done, here, let me say. So we take that yield data, we can model this, okay, and then through the mixture modeling in the EM algorithm, I get like a probability of assignment that it belongs to here or here. Okay, then I can take those probabilities and then model them with respect to climate variables. Right?
Okay, we're working backwards.
Yeah. And get at, like what you're saying, this rainfall, this and that. So I can tie the probability of an assignment into one of these two, to rainfall, to temperatures on certain days, threshold temperatures, and that's kind of
So
where...
there are good years and there are bad years, but
Yeah.
we're not going to necessarily impose a structure in the sense that they are identified with certain levels of rainfall. Rather, these states have, with certain probability, will come from one distribution or another.
Yeah.
So, in other words, rainfall will impact the probability with which
Yes.
they are in one side or the other.
Yeah. Now I could go one step further and put that inside the likelihood. Don't think it would converge. I think I'd have to go to a Bayesian type, some sort of approach to get something. Maybe not. I don't know. But pardon?
It won't converge.
Okay. But that's kind of, it won't converge with the Bayesian or without the Bayesian?
The Bayesian.
Without the Bayesian. Yeah, that's my hint. Where we've gone is, hey, let's look at these assignments. They should be correlated with weather because of just our thing. And sure enough, they have. And where we're going to go from there, not quite sure yet. Okay? So, that doesn't work. Okay. So, as I said, I'm going to estimate the rates of technological change in an upper and lower component, test to see if the technological change is different. What we find is in almost all cases that they are different. They're statistically significantly different. So that's interesting. We test to see if the probability of a state is constant, but we can't reject the null that it's constant over time, which surprised me a bit because I thought climate change and maybe some other stuff. But talking to, I forget who I was talking to, someone who's done something similar. They found similar results that they weren't finding big changes in extreme events or this or that. So that's where we're at. So the model intuition is producer's output is determined by the state of the world. There are J belonging to n finite possible states. Again, I restrict that to 2, just like everybody else with mixture modeling. Producer's output determined by kind of a 2-step process. Realized state J belonging to big J is determined by a random draw, and realized yield, okay, and this is my normal, the mixture of the one normal, is based on that. So, and these parameters may change over time. So, essentially in different states there are potentially different trajectories of technological change. And so that's what we're looking at. But backing up, and it doesn't seem, no one's really asked me this yet, but again, I'm not convinced on the idea of just measuring different rates of technological change in different parts of the distribution or different states. So anyway, so here's back to our illustrative example. And I want to show you how much it matters doing it one way or not. Okay, so this is just the regular trend. This is, and I'm going to show you the distributions, the mixture normals that come out of this with just one trend. So that's what's been done in the past. You model yields, yt is some function of time, then take those residuals and use a mixture, estimated mixture, okay, or do it inside the likelihood. This is with two trends, so they can be two different trends in the two different components. And I think the next slide, the next slide is the different distributions through time based on whether you use one trend or two trend. They're both mixture of two normals. Okay, here's using one trend, okay, and here's using the other trend. And so they're both mixtures of two normals. And what's happening is if you go back to this data, and the data, and this, it's a bit of a cat and mouse thing, chicken and egg thing, is that having two different rates of technological change explains heteroscedasticity that we see all the time in the yield data. Okay? Which makes sense to me. Okay? And so whereas this, using one trend, once you get to the distribution, that second distribution has to spread out to accommodate the heteroscedasticity, right? Whereas this, the two subcomponents, there isn't heteroscedasticity in those. What's causing the heteroscedasticity in yield data is the separating of the means of those two distributions. And so when I say it's like a chicken or egg, is heteroscedasticity causing what I'm modeling? Or is two trends causing heteroscedasticity? Incorrect. Go ahead.
So I just want to make sure you're fitting a single trend model with heteroscedasticity against a two trend model without heteroscedasticity.
Both with mixtures. Both with the distribution being a mixture of two normals.
I see. So they're both mixtures of two models, but here you're imposing a linear trend, the same linear trend in each.
Yes.
So here you're modeling.
Yes. Yeah. Yeah.
And now on the right-hand side, you're not allowing a trend in the mixture parameter. So basically on this right-hand side, so that you've got five
This is what's
parameters.
common done in the literature, yeah. Yt is equal to some ft plus epsilon t. Epsilon t is some lambda normal mu1 sigma 1 squared plus 1 minus lambda normal mu2 sigma 2 squared. That's what's commonly done. The difference is this, the second one is yt is distributed lambda, normal alpha 1 plus beta 1 t sigma 1 squared plus 1 minus lambda normal alpha 2 plus beta 2 t sigma 2 squared. And that's what's never been done. People have used the mixture. That's mu1, mu2, yeah. But this, I mean, it's flexible enough to accommodate. This is a mixture of two normals. I'm just adding parameters here. And then testing, right? And because I'm testing this equal to this, it's not at the bound, so I can use regular likelihood ratio tests, which you can't usually if you're testing one component versus a second component because you're testing on the boundary, okay? But that's not what I'm doing right here.
And earlier you said you found no change, systematic change in the probability of states. Basically, when you try to parameterize lambda with respect to time, you're saying you didn't find any trend there, right?
Right. Well, yes and no. I'll show you exactly what I did. Okay. So, and again, convergence issues. We got convergence most of the time. We looked at a bunch of crops, a bunch of things. I'd say 95, 98% of the time. But there are convergence issues that I think we've tried a third thing, and convergence went way down.
So is this a person being motivated because you only have one observation per year? Or do you have?
No, I have one observation per year.
Okay.
This is a county.
Okay.
I have one observation per year. I'm looking at county data. Farm level data would be better. If we went to national data, well, by then there's so much mixing going on that it's probably just a normal, so or close to it.
I'm trying to just get back to the question of the intuition of the two trends versus the one trend. So, in the single trend model, you have a catastrophic year. You get a bad draw. Next year, you have the same expectation.
Right.
In the two trend, it's less clear to me what you're.
Okay, okay. The two trend, here's how I see it, is that people are adopting seeds, more like racehorse seeds, that are going to do well. And so when they're in a good state, yeah, it's going up this way. But you know what? They don't do near as well of an improvement in a lower state, in a lower bad weather year, or this or that. And so the technological improvements in a lower component aren't going up at near the same rate. Okay, and in some sense, I think there's probably good reason with crop insurance around. If I can adopt a drug-resistant seed or a racehorse seed, I'm going to buy crop insurance and adopt a racehorse seed. That's what I would do, right?
So these two trends don't come from some farmers taking the conservative route, the robust variety that'll never hit the top. It's that you've got good years and bad years and more years.
That's how I see it, because it's at the county level, and so it's aggregated across the farms. I've applied it to some field trial data, just started applying it to field trial data up in Ontario over 30 years stuff. And interestingly there, we don't find the technological changes near as great, not even close as great. And the reason being, I think, is that when you look at county yields, what you have is attrition. You have a lot of poor farmers over time that leave, and not poor farmers, that shouldn't have been, that's maybe not correct, but farmers that are using maybe less technology, their land's incorporated by producers who are using higher end technology, and that's where you're seeing some you're seeing such greater strides in technological improvement than that's my explanation, than what I'm seeing when I look at just farm, and I've only looked at trial data on experimental farms. When I look at that data, I don't see near the technological change over time, the rates. And you're nodding. I don't know if you're experienced with that data.
You're seeing the managerial change, the effect of managerial changes when you're looking at county level yields versus trial level, field trials, you're getting presumably much less variability in management styles.
Right.
And so like you said, there's a survivorship bias in county level. So I think that's more down.
Where's my slide?
Can you get to the distributions?
The next one?
Yeah. So if I'm interested in only, say, adverse selecting against the RMA, and I'm not interested in exploring heteroscedasticity or looking at different, I just want adverse selecting against RMA, would this approach be better, more advantageous than using just a cured kernel?
Yeah, okay, well, I'll get there, okay? I know you didn't read the paper, that's cool. You think my student would read my paper? Just a hint to all the other students out here. Just a hint.
I haven't read your paper.
No.
Just to be clear. But so when I look at that left, I mean, that obviously looks pretty standard out of a lot of literature, regardless of the mixing. And, the first thing I look at when I see your left plot is, gosh, log that.
Pardon?
Is take a log to reduce the heteroscedasticity.
You can do that.
Does that normalize those distributions? Yeah, transform it. Does that normalize those distributions any?
It would a bit, right? It would a bit. To what end? Just so we can say it's normal? I mean, to what end?
Because to think about those deviations in percentage terms versus the deviations in...
Yeah, I mean, if that was your question, then that would make sense to do a transformation like that. So, yeah. Okay. So just looking at those distributions, even though they're the same, you're using mixture of two normals in both cases, there's a significant difference, getting at your question, in the rates. there's a significant difference in those rates. And so, I don't think this is really a trivial question of whether we, this technological change and how we measure it, particularly with respect to rating crop insurance contracts. And we do a lot with county yields now. We have GRP, GRIP, GRIPH. That makes up a pretty big amount of dollars now. And now we have shallow loss programs probably coming in that are also based on county or area yields. So, yeah, these are significant changes in the rates, but I do get into that game later on, okay? Okay, so the model to be estimated is just actually what I wrote down here. So that's what we're looking at estimating, okay? And we use, I've already explained it basically, this probability, the upper state intercept for the lower technological change, the variance, and this and that. And we looked at putting in heteroscedastic variance. It didn't, they're not, and even when you look at the data, it isn't. So, okay, so mixture models of two normals is quite flexible, can accommodate all sorts of non-parametric distributions, so getting at what you were asking, Abdul. So here, I just plotted, and I wanted to pick out a weird one, so I did. So these are actually in Ontario. But here's the non-parametric estimate, and here's the mixture. And so you can see as I go through that the mixture of two normals really is very, very flexible, can accommodate a lot of things, and looks pretty similar to the non-parametric estimates. So I don't think by using just two mixtures that I'm not picking up some structural shape that's in the yield densities because I'm only using 2 versus 3, 4, or whatever. So, okay. So, a couple of caveats. I've talked really about these. Realized yields are a function of adopted technologies, not necessarily the set of all possible technologies out there, right? So anything I talk about is reflective of adopted technologies, okay? And how to use county level yield data, would have liked to use, and as I say, I have some experimental data, but I still think actually it might make it more relevant in the area of crop insurance. So, there we go. And the crop insurance, despite what I said, and I work in the area, as Ian said, didn't motivate this at all. I was looking at climate change. Essentially, when you go back to this model, it's pretty flexible, and I can ask all sorts of questions with respect to climate change and start putting climate variables in this to get at lambda and things like that. And I can look at, hey, is the probability of these components going to change? I can simulate this thing and look at climate change. That climate change affects the probability of a given component. That climate change is affecting the rate of technological change in a component or the variance. So I can get at a lot more detailed questions than I would otherwise be able to with another model. And so that's really the motivation that got me to this model. So, question?
Is there any attempt to, if we just think about that way, so rather than do the mixture, actually, do the mixture a different way in terms of mixing the mean? Mm-hmm. So, I know logitech models will parameterize it, or will assume distribution, so like the mixed logit.
Yeah.
Have you thought about that? So thinking about the trend parameter changing over time, changing with climate conditions, rather than the mixture probability, so you only have 2 states in the world.
Right.
You could have an infinite number of states in the world by...
Yeah, getting there with trying to, it's gone. Trying to parameterize these things.
Yeah.
And stick in climate variables and have them in there. Right. And so, isn't that what you're suggesting there? Yeah.
But
Step 2.
A distribution for those too.
Pardon? Yes. Yeah. And so, and that's why I'm thinking I might need to go into a Bayesian framework. Right. So. Okay, so here's the data I applied to. So for Ontario, I have 32 corn, 6 soybean, and 25 wheat counties. Partially, they didn't grow soybeans up there in many counties till recently. And this is up in Ontario. And frankly, the data you have in the U.S. is so much better than the data we have in Canada and your access to it. That was one of the shockers of moving to Canada. I could not get, I had to construct from paper copies county level yield data going back. They did not have it. The province, the feds, nobody. I couldn't believe it. Anyway, unlike NAS, which is great compared to nothing. It is. It's good. So I shouldn't say that. I didn't do it. I had a student do it. So anyway, so we're looking at Illinois, Indiana, and Iowa for corn and soybeans, and then we picked these places: Kansas, Nebraska, and Texas for wheat. So 854 crop county combinations that we looked at. We excluded some very few counties with incomplete yield histories, quarter to 11. And essentially, these are main counties for these crops, so they make up a good part of. They're the relevant counties to look at.
You have it in 11 videos.
Yeah, I know. Okay. So here's our two empirical questions. Is there a statistically significant difference between the rate of technological change in the upper and lower states? And what I'm comparing is beta 1 and beta 2. Okay? And then, is the probability of being in the upper state stable over time? Basically, each observation gets an assignment here. And I'm looking, does that change over time? And so if the probability of being in the upper component is growing through time, then this will be getting higher. So I should see that in the data, in the results. Okay, so is maximum likelihood, we want to know the parameters. You know, this would be very easy to estimate if we could actually assign that, okay, these data come from this state, these data come from that state, then it's really trivial to do because you just take that data and estimate those parameters in the state. We don't have that, we don't know that, there's no way for us to know that, and this is common in mixture modeling, and so everybody uses the M algorithm, which I had not used before, but it works really well, actually. I was pleasantly surprised with it, and I'll show you. I think I have a bunch of pictures here to show you. So if you're not familiar with the M algorithm, essentially what it does is assigns a probability to each observation being in this component or this component, okay? And then estimates these parameters using like a weighted likelihood, essentially, okay? With the weight being a function of the probability that it belongs to that component, okay? And then goes ahead and does it for the next component, and then just keeps iterating until convergence. That's essentially it. So
it converges to maximum likelihood, right?
Yeah. So there's an expectation step, that's getting the probability, and then there's a maximization, just like what I said, okay? And then after you maximize, you go look at the data and recalculate those probabilities, then re-optimize, and you just keep going. So I got some really neat pictures. I thought they would be coming up. Again, I want to talk about this. Therefore, I don't have to say that it's either in the lower component or upper component. It's just like another maximum likelihood in the sense that you don't say that this observation comes from the tail. You just estimate the parameters, right? So people seem to be uncomfortable with that. Okay, so let me explain what this is. Okay, so this is the M algorithm. Okay, and so essentially here's yield data. I just cut it down the middle. Okay, you have to have the starting values. So you can do starting values either on the parameters or starting values on the assignment. So what I did is put, and this is common, anything below the half, anything below the trend, I said belong to the lower component, the probability 1, and anything above belong to the upper component. That's just starting values. And it really doesn't matter. I switched it, doesn't matter. Converges are the same thing. So, this is step 1, okay? And then I do the maximum likelihood, recalculates the probability, and you can see now the probabilities are changing. Okay, they're not all 0, 1, right? So it's making this assignment. It's doing the assignment, re-optimizing. And you can see this is...
These are probabilities of being in state.
And red,
upper state.
being in the lower state, and this in the upper, yeah. So I did it in color so you could kind of see it. I think it looks neat. Anyway, so nothing like good pictures when you present it. So anyway, you can see this is the same thing through time. Boom. There. So there we go. So you could see it go through time assigned to different ones. Okay. And that's where we, this is Clinton, Iowa, corn. And that's kind of where it ends up. And so, yeah. Anyway, so I was pretty impressed. I've never used the EM algorithm before, and it was neat to see it work, and it seemed to work, and I guess that's why it's adopted everywhere with mixture modeling. So, anyway. So this is a representative estimate. I think I have some atypical estimates. You know, we did 854, so there were a few that were different than what we expected, but we got something like this. This is soybeans. But again, the first one is how 95% of them look. Here's another atypical estimate. This is Hodgman, Kansas wheat. So here's what we have. 8.6% have faster rate of technological change in the lower state. So of the 854 that we did, okay, this isn't statistically significant. This is just what were the parameters. We had this being greater. Okay? 4.6% have equal rate of technological change in the upper state. 81.5 upper state trend is greater than 110%. I'm just giving you sort of some summary statistics of how much greater these were. And 68.4% were greater than 125%, 40% greater than 150, 16% were double. Okay? So, because there's 854, so I had to summarize it one way. Okay.
Alan, do you have some information about the technologies adopted in some of these counties?
Like what exactly is seized in this? No, I didn't go to the 800 and look at what the production practice. It's an amalgamation of a ton of things, right? Seeds, production, management, this and that. And no, I haven't gone and correlated that with them. Okay. So here,
can I
yeah,
one
please.
very technical question? If you did a random assignment of observations to get your starting point, rather than doing sort of a researcher split, would you end up with the EM algorithm end up in the same place if you just randomly assigned observations?
Yeah. What it may have done is, and you got to watch for this, right? Because these are completely interchangeable, right? So it may have when we look at these. It may put, call this the upper one, and this the lower one, but that's it. So it was amazing how well it worked. And then we went in another way we did it, and converged to the same thing, was essentially do the one trend, take those trend parameters, and stick them in here, and do the, do that, and use those starting values. So, but it's much easier to do the assignment starting values, frankly.
But you can't guarantee that you're not converging to a local outcome.
No,
That's always the problem.
and I say that, but, and you look through a lot of these, and you know this, we did this with all the trends we did. You look through them all, and you know, they all look sensible and make sense, but yeah, very little way to, what we didn't do is in the program run the code where we started at 10 different things, starting values, and then did that, but we did do 2 or 3 or 4, and we got to the same place.
But it would seem like a good test of robustness would be to actually do what Cam suggests with different random initial assignments.
Yeah.
They're all converging to the same place.
Yeah. No, that's a good idea.
Well,
That's
then
good.
just, again, get back up one slide. Maybe
Yeah,
don't
I
wanna
can.
hold you up, but if you,
No.
2 slides, that one there,
Yeah.
sort of, or well, one more.
One more. Okay, I'm getting there.
I mean, when you were showing this, again,
Yeah.
it appeared that the solution, the optimization point on the EM algorithm,
Yeah.
you had very few observations that were actually in the lower state
Okay.
as a relative percentage. Now, just a question would be, but that's because the county you picked.
Yeah, I guess so. Yeah.
I mean, that
Yeah.
suggests that, okay, so if you picked a county in which you had a lot more variation in sort of low states and high states,
Yeah.
it would be interesting to see how I mean, I'm not questioning the algorithm, I just, the sort of what happens when you start at one point. The memorials, it's a local,
Yeah.
and if you change it around, would it come to the same spot?
Yeah. No, that's it's a good idea. I could randomize it 10 times, and then I mean that's not uncommon. And then you pick the one with the highest likelihood value out of those 10, right? And that, yeah.
Should all converge to the same thing.
Right. Well, you can't guarantee that though, but
Well,
so
but you'd have a pretty good idea of the
yeah,
sensitivity
yeah,
of
yeah,
starting.
yeah. So, okay. Good point. Very good point. So here's sort of a summary. And, when I was looking over this last night, I thought, geez, this would be way better to do on a graph or on a map, in like a GIS map. But here's the ratio of the upper beta to the lower beta for corn is in the red. And you can see it appears for corn that the rate of technological change in the upper component is quite a bit higher than it is for the lower component versus soybeans and wheat.
What are these again?
Okay, this is the ratio of the upper, the beta U, so the rate of technological change in the upper, to the lower. Okay, so the 45-degree line is where they're equal. Okay, and these are the 854.
That's VU over VU.
Yeah,
So the parallel ones would be on that 45-degree line.
right. That's why the 45-degree line here. Okay, and for the most part, we see, like what I showed in the summary statistics, is that the BU is higher than the BL.
Going back to this idea of the transformable data, this makes the point. Would you think conceptually a bad state results in C fewer bushels being produced or C% lower production? Because typically when you talk to crop scientists, they think of bad states as one that results in C% lower production, not C bushel fewer production, right?
Okay.
And so right here, what you're showing is, and if you think about transforming that data versus not, if you think of typically a bad state being Z% lower, 10% lower production, right? If that's actually kind of the model in the production function, then you'd expect to see that higher state have a sharper slope or steeper slope than the lower state, simply based upon this difference in measurement.
Yeah, for sure.
And I'm not saying either's right or wrong, but when I talk to crop scientists, they tend to think of percentage terms, not official terms.
Okay.
They think there's kind of an inherent heteroscedasticity there in number levels.
Okay. Well, that makes Dan brought that up to me. I'm not a crop scientist. I'm not a farmer. so I just think of it in the data. You can, I mean, the point you make, so when it's a downfall and it's higher, for sure. Okay. So, here's the test. Here's sort of summary statistics. So, in corn, we reject that they're equal in 84% of the time. Soybeans, wheat, or soybeans 82, and wheat. So it's a pretty strong evidence, I would say, that if you buy into the model, first of all, again, no one's really questioning my model, and that, that there are two components and possibly different rates of technological change, that it's pretty strong evidence to suggest that they are different. If you're going to measure it and look at this in two different components, that the rate of technological change is different. And again, with that makes, intuitively, that makes sense to me. If I'm a farmer, I'm going to be adopting technologies not that worry about the lower tail, but help push mass up into my upper tail. I think, with the programs, the crop insurance, and stuff like that. Anyway, go ahead.
Maybe I'm misunderstanding
Yep.
your confusion as to why we're not questioning the model, but the model itself is, I mean, the single trend model is nested within the...
It is. You're right, and I reject it. I'm not trying to downplay my thing, but it's different. It's different. You're right.
I guess the strongest question in the model, I mean, so there was this debate back in the marketing literature in the 80s and 90s about whether you should have random parameters or latent classes. And there's one school of thought anchored by a guy over here at Fisher by the name of Greg Allenby that's that random parameters approaches strictly dominate latent class types of approaches in terms of best capturing distributions, and it would probably spill over to thinking about time trends as well.
Okay.
So there may, in terms of you trying to figure out how to justify the model, it might be good to go back and I can give you some sites
Yeah,
where,
I would like that.
where they kind of came out in that literature.
Okay.
There may be reasons why it's not applicable here, but...
Okay. No, good.
So Alan,
Yeah, 2 questions.
if you were talking in front of a bunch of Monsanto executives, right? Can you pinpoint? I mean, given that GM crops were a discrete change in the technology, are you able to pin down that those fast rates of adoption have led to a shift up into your upper?
I would think so. I would also think that
Are you able to pinpoint that in any way?
empirically.
Yeah.
Yeah, you know what could do is, and haven't got there, this is just beginning of a thing, is look at these different rates of technological change across, there's spatial correlation and everything, but I could look at farm numbers through time and correlate and look at that with respect to the rate of technological change, right? And there. So yeah, I think so.
What if you used 1% would be the rejection rates?
They'll go down, but not markedly. Not markedly at all. Okay? Yeah. Well, 1 second here. Okay, so this is, or if I can get at that. No, I don't have that, sorry. I thought maybe I did on a future slide, but I don't. Okay, and so summarizing hypothesis test 2, and where I'm going to, maybe I'll go to stay on hypothesis test 1. Okay, this is just it broken down by Ontario, Illinois, Indiana, Iowa for corn, right? I'm just showing the thing. And, it's pretty consistent through all these regions, the results, right? Now hypothesis 1, okay, for corn. So across, these 3 regions in Ontario, again, fairly similar results. Okay, now hypothesis test 2, I'm a little less uncomfortable with, or a little, less comfortable with, sorry. A little less comfortable with. Because here's what I did. Okay, essentially, I take lambda, it does an assignment through the AM algorithm, okay, and then I test ex post whether that's changing through time, okay? So, because those are lined up for each year with each observation. So I can get that, and I recover that, and then I can test to see if that's changing over time, and that's what I did there, okay? And what I find is that I'm not able to reject, majority fail to reject the stable expectations vector. I did it a bunch of different ways. This is just a t-test. I looked at, doing ranks and stuff like that. Results didn't change. In fact, ironically, this is, I don't know how many people know non-parametrics very well at all, but usually when you use non-parametrics like ranks or stuff, you're getting rid of the cardinality of the data and you're just using the ordinal part, so you're getting rid of some data. Okay? However, I found that it was actually adding information, which is really unusual, or you could think about it adding information, because these points were very close together in cardinal properties, but then by taking the ranks, I was separating them out when really there was very little distinction between some points of it being probability 0.985 and 0.986. Okay? And so I almost thought it was doing a perverse thing using the non-parametrics. The results didn't change, but that's why they're not up here.
Was your test, you took the lambda from each year and then ran lambda as a function of time trip?
Yes.
Okay.
Yeah.
In the EM algorithm, you can also, can't you also endogenize like lambda as a function of other things such as
That's
time?
where I think I need to go.
Okay.
Yes. Yes.
Isn't that
Yeah.
what suggested?
Yeah, it was. Yeah.
Brain point.
Yeah. And I can stick in time. I can stick in anything I want. Yeah. 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 This is sort of step one. This is relatively easy to do because instead of doing a weighted mean like you do in most mixture models, I'm just doing a weighted regression, right? And so, yeah. When you start parameterizing this stuff, you're asking a lot more of the likelihood part of the process.
But it's easier to parameterize your land output on exogenous conditioning factors than it would be to build it into the parameters of the normal, would be my guess.
Mm-hmm.
As a practical matter.
I don't know. I mean, I've also stuck weather variables in here, and that, it's just a weighted regression.
Yeah.
So this was actually trivial, sticking stuff in here. Sticking stuff in here, you're asking more, you're like the maximization procedure,
Yeah.
right?
It's actually harder.
Yeah. So.
Alan,
Yeah.
this result is
Right.
saying that the probability of low and high states have not changed.
Right. Which I thought was kind of surprising, frankly. I don't know, maybe they're changing, like technology's improving, climate change is pushing it one way or another. I'm not sure. So, because all we see is the resulting yield data, right? Many things can be going on, and this is what some of the questions are. Hey, can you get at that underlying stuff? Yes, please.
Is your conclusion that technological change is faster in high-yield states than low-yield states?
Yes. Not
That's
state,
just a
but...
truism, isn't that just a tautology?
No, if we all
High
started...
yield increases from technology, you're going to get high yields.
Mhm. But if we all adopted drought-resistant seeds, then the yields would start flattening off in the good years, and in the bad years where there's drought, we would get more, and we would see the reverse, right? So there are states you would see. In fact, I kind of thought we would see the reverse because I thought maybe people are adopting technologies that push the mass from the lower tail into the upper tail rather than adopting technologies to push the upper up.
Well, one of those new stacks is for more drought-resistant
It is.
corn.
Yeah.
So maybe that will push yields higher relatively in Kansas and South Dakota.
Now, I don't know this for sure, but I'm being told that those triple stack seeds aren't being adopted a whole lot. At least from the RMA perspective, when I talk to them, of people adding that component to their crop insurance and getting that discount. In fact, I think they've dropped it because they didn't see anybody signing up for that. And so, I went...
That seed is incredibly expensive.
Okay. Well, and you got crop insurance on the other hand.
$150 an acre just for seed. So farmers are a little reluctant to pick that up.
Okay. So I should go through this quick. So this is corn for the 4 different regions, very consistent. It's not like one region's dominating. This is Soybeans, of course, we only have 6 in Ontario, but consistent, very consistent across this. And this is wheat. And so, for the most part, the results are on the 2 hypothesis tests are very significant, very consistent across. And I think, as what we're getting in here, and what I alluded to earlier, looking at this type of model, and then taking it another step forward, and parameterizing these things in terms of weather variables, other stuff, will allow us to ask a lot of other hypotheses that I think are also very interesting and even more so. So here's what I meant by the stable probability belonging to the upper state. This is, I don't have what county, but this is similar to what most of the data looks like. Right? This is the probability of assignment. Okay? And as those distributions separate through time, we see them going to 0 and 1. Okay? And so, yeah, that's because of the data, I'm less comfortable with that second hypothesis. I need to put more thought into it. To your question, Abdul. So I did do an out-of-sample gain in crop insurance. Basically, I didn't compare it, to the non-parametric. I compared it to the 1 versus 2 trend to look to see if I'm using the 2 trend and RMA is using the 1 trend to rate, could I adverse select against them and make money? So this is this approach has been used in the literature. I've used it. I came up with it. So I've used it. Others have too. So anyway, I don't have a lot of time, so let's go to the results. So essentially, Illinois, Indiana, Iowa, this is corn. These are the results. They're not strongly significant, okay? There's no statistically significant results that show the 1 trend winning. There are statistically significant results showing the 2 trend. But you got to remember, we're just looking at the very lower tail. And so the power of this is low. It is. You're looking at a test that's just looking at comparing just the lower tail of these 2 things. And so the power is pretty low. Okay? And there isn't a whole lot of out of sample. This is out of sample. There's a whole lot of observations. And so this is corn, where we adverse select, and you can see the only one significant is where we do win for corn in Illinois at the 90% level. This is significant, I guess, down here. We win in Iowa. And we win most of the cases, but these aren't statistically different, right? We couldn't get statistical significance. And then wheat, and we win in 3 of those cases. And so we never lose, but the statistical significance isn't that great in this type of thing. And of course, we might not expect it because we're only looking at comparing 2 lower tails. Okay? So, I thought I had a summary thing. Anyway, on that test. So, crop yields are an important measuring stick of agricultural productivity. The crop science literature, or the plant science, when I gave this talk to a couple of different times to plant scientists, they're all over it. They think that these different components and being able to measure different rates of technological change and looking at the probabilities and connecting these, as you guys would suggest, is like, this would be fabulous if we can do this stuff. And this type of model allows us to do that. And I don't believe there's a model out there that has allowed us to ask these questions in the literature before, and I think they're interesting questions economically. So our conclusions is that we do have different trajectories in different states. That's statistically significant difference in 78% of the cases. Greater than 85% has a slower rate of technological change in the lower state. Inconclusive results. It's not like we're getting statistically significant results with respect to the probability of those components changing. I think the mixture model opens the doors for a lot of interesting questions, some of which you guys have brought up as well, and some of which, and we're pursuing some of those and trying to get that going. Results seem to be consistent with plant science research expenditures and things like that, and results consistent with stylized facts. It does produce heteroscedasticity, which we see throughout the whole field data. We're not seeing huge amounts of, as I said up there, of these probabilities changing through time, which, would we or not with climate change? Not sure. Results are inconsistent. You get very different results having two trends versus one. I showed you that for the crop insurance. If you're looking at those two different those mixture distributions, one trend, two trends, those distributions look very different. And if you were just looking at the moments of the data of the skewness and kurtosis and things like that, you're going to get very different results between those two things. So I think there's more to it than just looking at moments of the distribution and hooking them up with climate change. Results are fairly robust within a crop. And going forward, can we isolate the underlying causes of the different trends in the two states? This is what you guys were talking about. How different are the results at the farm level? We do have some trial data. What are the determinants? Again, these are the questions you all ask me. This is where we're going. What can we stick in here and model and stuff? So, yeah, that's kind of where we're going forward. Thanks. And I should point out the provincial ministry paid for part of the research, and the institute and the department paid for part of the research.
The people with no data.
Pardon?
The people with no data.
The people with no data, yes.
No data.
No data, yes. Sorry. The people with no data. Yeah, no. Yeah, I know. It's awful. Anyway, sorry. It took me 6 months for them to convince me they really didn't have this data somewhere. I just couldn't believe they didn't have this data somewhere. So.
Okay, we have the thank Alan at the end, so we have plenty of time for questions. Cam, then Luther, then who are you? Mario. Brian, did you have your hand up, Tim? Okay. So Cam, Luther, Mario, Tim.
Just a question on sort of where your research goes in terms of policy. So we all read from time to time these articles looking at the world food situation, technological change. You'll see these in The Economist and other Choices magazine, whatever. And one of the things they look at and they try to answer the question is, the population data, income data, and then they start talking about, well, given the rate of technological change measured in the linear trend model, then this is kind of what we see happening. Where do you, if we just accept your maintained hypothesis, if you will, where do you think how do you see your research influencing that kind of a discussion?
I do see it. I haven't gone into that, but and the reason being is, this is like 6 months old, and I'm just getting my head around it, and before I step into that bigger arena. But I am trying to collect data from around the world and trying to look at this model and what the implications would be versus what's going on with the one trend and what people are saying and comment on that. So yeah, I think it has relevance, and I'm going in that direction for sure. To comment, because it may have different implications than what's out there already. So yeah.
Looking at yield trends for the major crops on a worldwide basis or for the U.S., a linear relationship gives a beautiful fit for the long term, dating back to about 1960. Does your data refute that or shed any light on that issue? The argument is, are the yields increasing at a constant rate? They're increasing. An increasing rate or a decreasing rate?
Yeah, I think I can shed some light on that. One of the things, though, this model, once you aggregate the data to look at, like the U.S. national linear trend, and all of a sudden these components, because I think these components are made up of bad weather years versus not. And once you aggregate across space, then those components go away, right? In a county, there's still enough spatial correlation that everybody's either going to be, bad weather years probably going to affect most people. And so you're able to pick up these different components. And at the farm level, for sure, you would be able to. But once you aggregate, then it goes away, it's just a thing, and you really wouldn't be able to model these different rates of technological change at an aggregate level, despite at the farm level, there would be, okay? And so how that all works into all that is food for thought, for sure, the model. Yeah?
Going up.
Let's talk about N.
Let's talk about what?
N.
N. Okay, sure.
Okay, so with N equal to 2, with two constituent distributions in the mixture, you're naturally allowing for, or basically it needs for a bimodal distribution.
It could, but a lot don't, right?
A lot,
One is
well,
the mass and
there's a
the...
tendency towards that, they could sometimes collapse together, right? Okay. If you go to N equal 3, then you're getting a happy medium, right? And so my expectation would be as you go from N equal 2 to N equal 3, that the tails would become thinner. As a consequence, that the implied fair premium rates for insurance would further decline. Have you tested if we're using this to predict or to use it to compute premium rates for crop insurance, it would seem to me that you would want to do some sensitivity analysis with respect to N. At least go and take it out to 3.
Yeah.
Have you done that? I guess.
No. But I'm not, N equal to 3, I'm not averse to doing that at all, and it's a good next step to go.
Yeah.
N equal to 2 was a new step
equal
with
to-
this.
And you got a huge drop in implied premium rates.
Yeah,
And I guess you go into 3, you won't get as huge, but it may still be significant.
right. I would think it would. I would think it would. We've run N equal to 3 number of times and a number of things, just haven't put it all together.
Yeah.
Would it, if I recollect what the student found with N equal to 3 was that that probability was pretty low.
What?
Well, lambda 1, lambda 2, lambda 3, right?
In other words, it still wanted to go bimodal.
Yeah. So, but and if you look at the non-parametric estimates, it's pretty, it captures it pretty closely, right? And so, what more of the likelihood are you going to get for those parameters? Do you see what I'm getting at? Like you look at what our data tells you and stuff like that. I know what you're suggesting, and I'm not averse, and we'll go do it.
Yeah.
So, yeah. I think there was some of that.
I just want to push you a little bit on the issue of climate change, just your intuition there as to why you think that your results are not showing any effect.
Yeah, that might have been
It's just not clear to me.
too strong, but what I'm not seeing is that it certainly didn't show me that the probability of, like in Ontario, okay, climate change should help us. So that the probability of that lower component should decrease. And there is...
You're basing it solely on the fact that the selection is going on based on climate. That's,
but there's 100 things going
Right,
on.
that's
Right.
what I'm
Yeah.
saying.
No. There's 100, but certainly climate isn't so dominant that it's showing up, and that's what I'm trying to say. That's all. Nothing more.
I mean, in the case of that, adaptation is taking over.
Yes,
for
sure.
time.
Right, because all we see is the end yield. That's all we're modeling, right? And we can only see the result of the yield, okay? And so that's adopted technology. That's a bunch of things going in there, right? And those aren't all perfect. So, but hopefully we can get at parsing some of those out. And so, but I guess maybe I overstated, but what I'm trying to say is it's not so dominant that does that make sense? Yeah. Okay.
So would you still use this approach if you had a random sample of farms from each of these counties? Or would you do something like do a quantile regression in each county and just look at the first quantile is going really slowly?
You mean an unconditional quantile, not a conditional quantile?
Well, as a function of trend. That's
Yeah. If we've done the unconditional quantile, like FERPO and Econometrica, 2009, because the conditional quantile is on the residual, not cared about those, right? So the unconditional quantile, you see if you pick this, whatever this is for the lower component, and you run that quantile regression of this, it's almost identical. Unconditional quantile, right?
Okay.
Yeah.
So your lower here is like basically the lowest quantile, and then the rest is the average of the upper quantiles, basically. I'm just thinking visually.
Yeah. No, well, and then if you took this, let's say this is 0.15, well then there's 85% weight. But if you look, if you look down, maybe it's not exactly like at 0.1 or whatever, it's pretty close, right? So, yeah.
I hear that this method is very well for annual crops where technological change is measured from 1 year to another. You have unlimited resources of data. How do you propose a similar methodology, using this methodology with more capital and labor intensive crops, like for instance, fruit orchards, results are being seen in years to come, or sometimes they're not from 1 year to another. I mean, it will be possible with that kind of crop, or this framework just applies to...
No, I don't see why it wouldn't be. I mean, with the yield, you have your yield data coming out of that crop, right? And yeah, I mean, this is no different than what anybody else has ever done, other than I'm just adding another component to it, right? And so, just like you could have, you could estimate a trend in tree crops and get a distribution. I'm not doing anything different other than kind of adding another component to it and looking to see if that component, the parameters of that are different than the original component. So yeah, I don't see an issue with that at all.
Yes, the thing is, I was thinking that most of the things that you do in 1 year tend to accumulate and further on, especially when it's very labor intensive.
Right.
Yeah, in tree crops that are usually less labor intensive, you have to adjust the tea and it will grow eventually. But the fruit orchards are very labor intensive, and you don't see the immediate results. That's what I was asking.
Yeah, but how would that affect the yield?
Oh, yeah.
Right? And so, whether you do this now, an investment now, and then it starts growing 5 years from now, because the yield data is still going to be that, or you do the investment now and you get it right now. I mean, where it would be different is if you're trying to link up these parameters to capital investments. Then you would have to take into account that, hey, there's a 5-year lag, blah, 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 right? So in that sense, yeah.
Okay. Joe, we're here. I think you would have really enjoyed this seminar. Statistics, applied, and potential policy relevance.
And agriculture.
So, Alan,
Thank you for
thanks
having
very
me.
much for presenting in this seminar program.